Hi everyone, in today's video we're going to continue with the climb section of the general performance theory. In the previous videos we have talked about the angle of climb, what affects it, and basically that was the first very important parameter which describes the climb of the aircraft. And now the second one is the so-called rate of climb. And to roughly define what the rate of climb is, basically the rate of climb is going to be the vertical speed of the aircraft, or the vertical projection of the true airspeed. To understand this a little bit better, let's sketch the initial climb, or the climb segment of the aircraft, like we usually do. So we have a local horizontal, we have a flight path along which the center of gravity of the aircraft travels along. So there you have your flight path. We're going to have a local vertical as well, right? A local vertical, ZE axis if you remember. Okay, so between the flight path and the local horizontal we had the angle of climb, the gamma, and we have on the flight path, of course, the center of gravity of the aircraft, like this. And let's just quickly sketch up the airplane. Okay, but what's going to be even more important, and here we'll have to make a differentiation. So when we sketched up the climb so far, and when we've talked about the true airspeed with regards to its direction, we said that the true airspeed would be acting in the negative longitudinal direction of the aircraft. So just a reminder, basically, like, so here would be the true airspeed, and it would be pointed in this direction, so in the negative longitudinal direction. And here we'll have to make a differentiation in perspective. And what I mean by that in aerodynamics, usually, and this is where, again, relative airflow is going to be important. So in aerodynamics, when we look at objects, for example, airplanes going through a mass of air, how we examine the relative airflow is by the relative airflow basically coming onto the aircraft, right? So it's coming from the negative longitudinal direction of the aircraft. So we could say that the aircraft is sort of stationary in a given position, much like in a wind tunnel, for example, and the relative mass of air is moving around the aircraft, right? So in flight mechanics, and this is why it's important, because the two are equivalent. In flight mechanics, we're going to presume that the same exact thing is happening, generally speaking. So we have the aircraft, but the aircraft is moving through the mass of air with the same v velocity. So the v velocity is the same, it's just pointed differently, and so it's not the air mass which is moving around the aircraft, around the stationary aircraft, but actually the aircraft is moving through the, let's say, fairly stationary mass of air. And the difference, so the altogether effect, aerodynamically speaking, is the same, but why we have this differentiation is because in the first example we were interested in what the air does around the aircraft, and for that approximation it was more correct to use the analogy that the relative wind was basically, or the mass of air was moving around the aircraft, But now I'm more interested in the motion of the aircraft, right? How does the center of gravity move relative to the air, and of course, as we'll see later, relative to the ground. So this is why we have this difference in convection as to where the true airspeed of the aircraft is pointed. So with this out of the way, and we're going to use this one from now on, generally speaking. So here we're going to have, in that case, the true airspeed. So the true airspeed, of course, would be a vector. And if you just want to describe it with regards to the Vx, Vz, Vy, so in the coordinate system of the aircraft, you would say that it would be a positive Vtas 0, 0. Okay, but what if I wanted to look at the components in the local horizontal? So this would be two perpendiculars, right? So this one is this axis is parallel with this one, so this is also a local horizontal, and I also have a local vertical, right? Or you might have the local vertical here as well. This is going to be perpendicular with both of the legs as well. So I'm interested in finding out. So this we could also call the XE axis, and it's generally be pointed in the northern direction. So this could be the XE axis of the Earth coordinate system, the longitudinal coordinate axis of the Earth coordinate system. And what if I wanted to find out the basically the projections of the true airspeed into the vertical and into the horizontal axis? So I'm going to break into two components. So this would be the horizontal component of the true airspeed, and we would have a vertical component for the true airspeed. Okay, and since we see that the true airspeed is parallel with the flight path, and the horizontal component is parallel with the local horizontal, of course, then we're going to see that the angle between the true airspeed and the local velocity component is going to be the same as the angle of climb. Right? It makes sense. We're basically using this rule right here, is that if you have, just 1 second, if these sort of legs are parallel to each other, and this basically leg of the triangle is common. In that case, if this is an alpha angle, this is going to be an alpha angle as well, right? Okay. Okay. So if I want to magnify this one right here, we said in the beginning that the rate of climb is going to be the vertical component of the true airspeed. So basically this one. So this is what we're going to call the rate of climb. And how we can calculate the rate of climb, to understand that, let's sort of magnify this problem and take it a bit further down. Okay, so we said that we have the true airspeed. Just 1 second. You have the true airspeed, which looks like this. True airspeed, or actually let's index it with Vtas. True airspeed. You have the rate of climb, which is the vertical component, and so this is the rate of climb. And you also have the horizontal component, which looks like this. And of course, the angle between the horizontal component and the true airspeed is basically the angle of climb. Okay, so to calculate the rate of climb, we're going to need the sine function. So the sine of gamma is equal to the rate of climb, so the opposing sine over the hypotenuse, which is the true airspeed. And from this one, we can express the rate of climb. So therefore, the rate of climb would be the sine of gamma times the VTAS. Okay, so from the previous episodes, basically, we already know by now that if I wanted to express sine of gamma from the climbing phase, if I wanted to express it with the forces, what I get is the thrust minus the drag over with the weight. So I can substitute this value into the formula for the rate of climb, and what I get is that the rate of climb is going to be the thrust minus drag over with the weight times the VTAS. Okay, I can take this one step further. So it's basically the excess thrust over with the weight times the true airspeed. What I can do is I can multiply each of the forces with the true airspeed to get it into like one big expression. So what I'm going to have is the thrust times the true airspeed minus the drag times the true airspeed over with the weight. Okay, now I have two very interesting expressions right here. Okay, so thrust times velocity and drag times velocity. Just one quick detour here. What was force times a velocity equal to? What kind of physical mechanical expression does that give us? So if your, I hope not guess, but answer was that it's basically power, then you were right? So power is equal to force times velocity. So therefore we can see that this expression right here is a power, and this expression right here is a power as well, right? So we have already talked about these two kinds of powers. So what kind of power does the thrust times the velocity give me? What we said is going to be the so-called power available, right? It's going to be the so-called power available, and the other one, the drag times the VTAS, is going to give us the power required. So if I plug these two up here, what I'm going to get is that the power available minus the power required over with the weight equals rate of climb. And let's just write this in a sort of bigger formula right here. So these two parts, because this is the final formula. So the rate of climb is the power available minus the power required over with the weight of the aircraft. And this is a very important formula that we're going to use a lot. Is equally as important as the angle of climb or the sine of gamma formula, right? So there you have it. The rate of climb is dependent on the difference between the power available and the power required and the weight of the aircraft. Okay, so what we're going to call this power available minus power required is going to be known as the excess power available, and it does a very similar job to what the excess thrust did to us during the climb, or when we examine the angle of climb, basically, right? So this is the excess power which is available to us. Okay, so therefore we can see again that the rate of climb is the local vertical component of the true airspeed, right? And we can calculate it with the help of the excess power available. So the power available minus the power required over with the weight of the aircraft, right? And this rate of climb is also a velocity, so it's also referred to as, so the rate of climb is also like vertical speed. And the dimension for it, the most usual one in commercial aviation and the one which you will see when you start flying, is usually the feet per minute. Is also indexed in aviation books like this. So FPM, it means feet per minute. And also if you have flown maybe post, like, or actually Soviet Union era gliders or even powered airplanes, on some airplanes they have meters over second, this vertical speed. So this is what they have. So this is because, yet again, the rate of climb is a velocity, is a vertical velocity, and it's vertical with basis basically to the Earth's local vertical, right? So not in the aircraft's coordinate system is what I'm trying to say. Okay, so so this is it. Let's start to take this a little bit further and define the speed where the rate of climb is going to be highest for any given airplane. So this, you remember that for the angle of climb we had a speed where the angle of climb was greatest, and that was called Vx. And if the pilot maintains the Vx, they're gonna get the best angle of climb from the aircraft. And so now what we're going to look at is the speed where the rate of climb is going to be greatest at any given point. And this is going to be defined as the so-called Vy. And the Vy is going to be the speed for best rate of climb. Right? So this is going to be the speed for the best rate of climb. Okay. So, let's start examining first off the jet. Where is this Vy for the jet? So to understand that, we'll need to basically understand what this rate of climb is a function of. So it's a function of the weight. It's not going to affect with regards to the type of propulsion, the Vy, as you can see, because it doesn't matter whether you're a jet or propeller, weight is weight, right? So that's not going to affect for us the rate of climb pretty much. But what's going to affect the rate of climb on the other side pretty heavily is this excess power available. So to understand how does that change for the different types of propulsions and with the different influencing factors that we're going to have a look at, we'll need to basically plot the power available and the power required for these different kinds of propulsion. So let's go ahead and do exactly that. Okay, so we're going to have, in this case with regards to true airspeed, because this is what we said that we multiplied by, so we multiplied by the angle of climb times the true airspeed, so we're going to plot everything in true airspeed. Okay, and we're going to have power available, and we're going to have power required as well. Okay, so if you remember, like we presumed for the jet, the power available, not just for the jet, well, the power available is the thrust times the VTES, so the true airspeed. So we presume the shape of the thrust curve to be a constant for the jet, right? So it's a constant. If I multiply it with an increasingly growing amount, so the true airspeed, what kind of a function do I get? We will get a linear function, right? So in zero, true airspeed is going to be zero, and it's like continuously increasing. And this would be your power available for the jet. Okay. So the next one, which we're going to have a look at, is the so-called power required, right? So the power required is basically the drag times the true airspeed. So it has a very similar shape. It's just a bit steeper, we could say. Well, it's a bit thicker on the other side, however. Approximately looks like this. So this would be the power required from the jet. So it has a few interesting speeds for us. Of course, at the minimum point, what you would have is the VMP. And what you have in the tangent of the function is the well, I drew it to be a little bit flat, this curve, but you can see that it's approximately right. Oh, sorry, it's approximately a bit right of the VMP, so it touches the curve somewhere right here. So this would be your VMD in this curve, VMD for the jet, which is 1.32 times the VMP. Right, because it's in the tangent, it touches the curve at one point. And so when we look at the excess power, like this is the area. So the area in between the power available and the power required is the area where we're going to be examining the excess power available. So this area approximately right here. So this is the area, and the excess power available is always at any given velocity or speed, basically, is this expression right here, right? So at this velocity, this would be my excess power available, because it's the power available minus the power required. So power available minus power required at a given speed. Okay, so I'm trying to optimize this value, so to speak, and I try to find the velocity where this excess power available is the maximum. And it's not easy to see from these sort of shapes, but generally speaking, and we'll just have to sort of remember this, is that usually it's somewhere here in the middle. But there's few things that we, let's choose another color because this is not very visible. Much better. Okay, so generally speaking, this power available minus power required maximum, so the place where it occurs usually is higher than both the VMP and both the VMD of the jet, right? So it would be, this would be the Vy for the jet. This is the Vy, and as you can see, this Vy is going to be higher than both the VMD, and of course VMD is higher than the VMP. Or actually, this is dependent, so the shape of all these curves is very much dependent on the thrust curve and everything, and the power required, so which is going to be a function of many things. So there's a possibility that this could be equal, but it's continuously changing, and generally speaking higher than the VMD. So what we can see is that the Vy for the jet is going to be higher or equal than the Vx for the jet, right? Because if you remember, for the jet, the Vx, so the speed for the best angle of climb, was equal to the VMD, right? And this is where the highest power available minus power required function is. So therefore, that's where you have the highest excess power available, so therefore the highest rate of climb with the jet. Okay, so I hope that makes sense. And we're going to go on to examine the case for the propeller-driven aircraft. So let's examine the case for the propeller-driven aircraft. Okay, so we're going to see again, here you have the rate of climb, just to sort of memorize it even further. Rate of climb was power available minus power required over with the weight. Okay, so what we can see here is that this is going to be dependent on the excess power available as well, right? So the weight is the weight. There's nothing much we can do about that. So let's just plot the the power available and the power required curves for the propeller-driven aircraft. And this is why we mentioned initially that it's very important to understand and remember the shapes of these curves, because it's going to be used very, very frequently here. And I would just strongly advise, if you are not so familiar at this stage with it, to just go back and review them until you have, I would say, a fairly high comfort level with them, so you're pretty familiar with them. You don't confuse the power available and the thrust curves and the jets curves with the propeller curves. It's I would say it's very easy to think that you're familiar with these curves and then go ahead and screw them up, because it's easy to mix them. So if you're not familiar with them, I would just strongly advise that you look at those diagrams which we sketched up on the end section in the classroom training center, just get more familiar with them. Okay, so here you have we're gonna have the power available, the power required curve. And so the power available, if you remember, for the propeller one, looks a bit like this. So this whole thing is shifted to the right, like this. This is the power available. And for the prop, and we have the power required. Which looks like this. This would be your power required for the prop. Okay, and of course here we have the stall speed. Right, here we have the stall speed, and here we're gonna have we haven't mentioned in the previous one the so-called Vmax SNL, so the maximum straight level speed. Okay, so we're also going to have the VMP, the minimum power speed, and we're going to have the tangent to the curve somewhere right here, and this would be your VMD, right? So approximately 1.32 times the VMP. Okay, and so you can see that on this curve as well, the excess power available is going to be in this area, right? So the area between the power required and the area between the power available, right? So this area right around here. So at any given velocity, yet again, so let's say this velocity, if you want to look at the vertical projection, the distance between the power available curve and the power required curve would give us the excess power, right? So the power available minus the power required would be your excess power. And so in this drawing, where is it, the maximum? And generally speaking, for a turboprop or any propeller-driven aircraft, basically, the Vy, so the speed for the best excess power, is going to be faster than the VMP, and so faster than the VMP, and in the region of VMD at low altitude, so around the VMD at low altitude, and generally speaking, as altitude increases, it's going to be slower than VMD, and we're going to see why that is. It's basically a shift in the power available and the power required curve with the shift of altitude, but in the general cases, this best excess power available is going to be somewhere right here. So it's between the VMP and the VMD, but it is slower than the VMD, and as altitude increases, even slower and slower. But this would be, yet again, your Vy for the prop, and it's visible that it's going to be slower than the Vy for the jet. And this is going to be your maximum excess power available. This is the maximum, right? So we can definitely see here as well that the Vy for the prop is also going to be bigger than the Vx for the prop. And this is going to be like a general scenario. It's the same as for the jet. So in most cases, or not in most cases, in all cases for any airplane you might happen to fly, and of course, you know, yeah, any fixed wing aeroplane, you will see that the Vy is faster, so the speed for the best rate of climb is faster than the speed for the best angle of climb, and this I cannot emphasize enough. So the speed for the best angle of climb is therefore slower, always slower than the speed for the best rate of climb, and it's very actually it's a lucky coincidence, but from flight technique wise we'll see that why this is so great for us. Okay, and we're gonna continue from here with the factors basically that affect this rate of climb. But before we do, just a quick recap on what we have done so far. We have defined the rate of climb as being the vertical component of the true airspeed, and we also saw that the way we calculate it is the power available minus the power required over with the weight. So we're looking at this side of the equation, and so therefore we said that this is going to be the influencing factors is going to be the excess power available over with the weight of the airplane is going to influence the rate of climb. And we saw that, and we also defined the Vy, so the speed for the best rate of climb, and we saw that for both the jet and both the propeller-driven aircraft, the speed for the best rate of climb is a speed faster than the speed for the best angle of climb. And this is where we'll continue from.